Hi, good morning everyone. Welcome back to Operating Systems. I'm recording a video lecture today since I'm away giving a guest lecture in California. Today I'll be talking about chapter 37 in the OSTEP book, which is all about physical hard drives. Now, for about 40 years, the hard drive has been the storage device of choice for almost every size of computer, ranging from gigantic mainframes all the way up to tiny laptops. In fairness, the hard disk is starting to be supplanted by the solid state drive, but that replacement hasn't happened completely yet, and it's going to be going on for at least another decade, I suspect. And furthermore, the newer solid state drives all attempt to emulate what a physical hard disk looks like. So it's important to know how these physical devices work. Now, internally, a hard disk drive is exactly what it sounds like. It's a couple of disks, these circular platters here. In a large hard drive, there are going to be several disks, each one of them known as a platter. And all of these platters are mounted on a common spindle that is driven by a motor that makes the entire assembly go around at a constant speed. And a common speed for this to go around is 5,200 revolutions per minute. Now, when the hard drive has been idle for a long time, that motor will stop. You can hear that in a computer when it goes zzz. But most of the time, whether it's being used or not, it's just constantly spinning. Whether it's being read or written has to go around at a constant speed. Now, each one of these devices is a steel platter that's been coated with a nice polished surface, and it is magnetizable, meaning that if you take what's known as a little read-write head, it's a little magnetic ferrule that you put right on the platter and run a little current through it. By creating a magnetic field, you can make a little spot on that disk in which the magnetic orientation of the molecules are either pointing all up or pointing all down. And so that can represent either a 1 or a 0 at any little position on that disk. Now, perhaps it's obvious that we're not going to go out and make marks in arbitrary spots in that disk, but rather we have to organize it with some structure so that it's easy to get a large amount of information on and off a disk. So if we look at any one of these platters, what we're going to do is divide it up by its geometry. So what I can do here is divide this up almost like a pizza to little slices. Notice my slices aren't quite even because I'm trying to maintain perspective, but you get the idea. And then we can also make circumferential ovals here, circles in the real thing, and divide this disk up into little sections. Maybe I'll give one more here. All right, and if we look at any little one of these things here, one of these is called a sector on the disk. If we take a complete loop of sectors going all the way around the disk, and one set of sectors going all the way around the disk is known as a track. And now each sector has enough space in it that we are able to record traditionally 512 bits of information into that sector. Now, it just so happens at the hardware level, a sector is often slightly larger than 512 bits. Oh, I'm sorry, no, it's not bits, 512 bytes. My bad. A sector is 512 bytes. At the hardware level, it's usually slightly larger than that. The hardware will often encode some extra bits that will be used as a checksum to verify that the data is good. And there are also some bits there to mark the stop and the end. This is called the framing. But for our purposes, we'll just talk about 512 bytes per sector. Now, how do we get data on and off the disk? Well, I'll draw it on this second platter here just so I don't overlap everything. What we're going to introduce is a little mechanical arm that sits right over the surface of the disk and can move back and forth in and out towards different tracks. So you can imagine this mechanical arm sitting out here, goes out here, and at the end of the mechanical arm is a little magnetic read and write head. And here there's a little stepper motor. That can move that arm back and forth so that the read and write head can move to any track that it likes. So given a little time, we can move that read and write head to read and write any sector that we like. Now, there are multiple platters here, and you can think of there being multiple read and write arms, sort of like fingers on a hand, that all go back and forth at the same time. So there's one read-write head on the top of this platter, and one on the bottom here. One on the top, one on the bottom, one on the top, one on the bottom. And they all move back and forth at the same time. All right, so now, between the combination of this read-write arm moving back and forth, and the platters going around and around, we should be able to select any sector on the disk that we want to be able to read. Now, what makes disks interesting is that because they're physical devices with moving parts, it takes time to access any particular element of the disk. So if I want to get this item over here, that sector over on that part of the disk, there's at least 3 maneuvers that are going to be necessary in order to get that item. So, number 1, we're going to have to move this read and write head back and forth till it gets to the desired track. And this motion is known as the seek time. Number 2, this disk is constantly going around in a circle at 5400 RPM, and the sector that we want is not necessarily going to be in exactly the right place as soon as we move that arm. So once we move the arm to the right place, we have to wait for that platter to come around to exactly the right spot that we're ready to read the sector that we're interested in. And this is known as the rotational delay. Finally, once the disk is moved to the right place that we're ready to read the sector, there's a certain amount of time that must elapse for that head to pass over the sector and either read that information off the disk or encode it onto the disk. Now, if it's just one sector, that amount of time is going to be relatively small because that disk whizzes by very quickly. But if we're going to read a large amount of data, maybe 10 or 100 or 1,000 sectors, then it is going to take some non-trivial amount of time for that disk to go by. And this is known as the transfer time to read that data off the disk and give it back. Now, before we go any farther, I want to show you some real disks. This picture applied to disks that were used as far back as the 1950s and the 1960s. And the earliest disks were measured about 1 foot in diameter. So when you turned on a computer, there was a gigantic motor that had to really move a large amount of mass around in order to get that thing going. As time went by and disks became more of a commodity, they became smaller and smaller so that A, they're faster. They might be a little bit smaller, but they're, because there's less physical stuff to move around, they can spin faster and their seek times get smaller. In the 1980s, the most common size of a hard disk was about 3.5 inches. That is the radius. That's the radius of the disk. Now here's a disk. Here's an old disk that it's quite ancient. It only has, let's see, how many megabytes does it have on here? It doesn't say how many megabytes it has on here. It's called an ST251. And so I opened it up to show you what's inside. So up here you can see there's a picture of a disk. Right here, over here we have the platters that spin. If I turn it on the side, you can see there's multiple platters on this disk. It has 3 of them. And then right over here is the read-write head. You can see there's a motor down here, which is what moves the arm. And the arm can slide back and forth so that it can reach any track on the disk as it spins back and forth. Now, by the way, don't do this to a disk that you care about, because this a hard disk is a high precision machine that depends on exactly the right amount of air buffer between the read-write head and the platter. In fact, a disk, you can see there's a little round gasket around here, a little rubber gasket around here. A proper disk is constructed in a clean room factory and then sealed up so that you don't have dust and all sorts of gunk getting in there. And once you open it up like this, the disk is ruined and it's never gonna run again. So if you have an old computer with a disk you don't care about, it's kind of fun to open it up and see what's inside, but don't do this to something that you care about. Now, this is a 3.5-inch disk, and over time, disks got smaller and smaller. No, I'm sorry, I misspoke. I was looking at the wrong one. 5.25-inch disk. This is what I'm talking about. And then over time, they got smaller and smaller. This is a 3.5-inch disk that was in common use in computers in the 1990s. And then they went down to 2.5-inch disks, and these started to be used in laptops and other portable computers about the turn of the century. But you can see that internally, it's exactly the same structure. There's a little platter that spins, and there's a read-write head. These very small disks typically only have one platter in them because you want them to be really flat in order to fit into your laptop or other mobile device. Now, in the early days of operating systems, all of this complex geometry was exposed to the operating system, and every operating system had to know exactly what is the geometry of every disk. How many sectors of it has, how many tracks does it have, how fast does everything move. But over time it was learned that this was not really scalable in terms of the effort necessary to keep an operating system up to date, and disks have gotten more sophisticated in recent years. So here's the picture of how a modern disk attaches to an operating system. So here we have a platter and our seek arm of the physical disk itself. Now, the physical disk itself just has a couple of wires coming off of it that are there to control the motor and the disk arm and the data going back and forth. But instead of exposing that directly to the machine, disks today have a fair amount of onboard circuitry that will manage all of these details for us. So attached to this disk is a small controller that has a little CPU of its own and a fair amount of memory that serves as a buffer cache, and an interface to the outside world using a protocol like SATA, serial ATA. Now, whenever the machine wants to request data from the disk, it doesn't go directly to it and tell it exactly what to do. Instead, it communicates over a bus, in this case the serial ATA bus, to a controller device that sits in the computer itself. Now, the controller device is going to be on a general purpose I/O bus, like a PCI bus. And then this PCI bus is eventually going to interface with the main machine itself that has its own CPU and RAM and everything else we would find in a modern machine. Now, why do we do this? Well, one reason is just generality. We don't want the machine and the operating system to worry about the details of the geometry of this disk here, because we want to be able to simply plug in any disk and expect it to work. But the other is performance. So the way that this controller communicates with the disk itself is by issuing a series of commands in packets. So you can think of little packets of information flowing from the controller down here, and then responses coming back this way. And each one of these packets conveys what the controller is asking the disk to do. So one type of packet might say, read from block N. That's a request we would send to the disk. Another might be write to block N, along with some data. And a response that could come back from the disk might be, here's the data corresponding to block N. Now, what's handy about this is that the controller is able to send to the disk data as fast as this little controller over here can receive it. And if these requests come in faster than this disk is able to handle them, well, they'll simply just pile up in the buffer and await service. Likewise, data becomes available on the disk at odd intervals, right? This disk is spinning around, the arm is going back and forth, and it's difficult for the machine to predict exactly when this data is going to come back. So when data is read out, it goes into this buffer here until there's an opportunity to send a packet back to the controller, and the controller is able to receive it. In other words, this whole process here is asynchronous. Remember, asynchronous means out of time, which is to say the controller is going to send packets whenever it wants to. The disk is going to send packets back whenever it wants to. And each side has a buffer so that it doesn't have to be immediately prepared to deal with the action that is requested. Now, the performance aspects of this are pretty interesting. So there's a big mismatch between the performance of the main computer up here with its RAM and its controller and the physical disk down here. As a rule of thumb, you can estimate that a typical hard disk drive takes about 10 milliseconds to perform one seek. Now, that should seem like a large amount of time to you. After all, if we can modify memory in nanoseconds and a disk moves in milliseconds, that's 6 metric orders of magnitude between the access time of memory and the access time of disk. And in the worst possible case, if it took us a millisecond every time we wanted to read one sector, we'd have an awfully slow disk. How slow would that be? Well, let's see. A sector is 512 bytes. And if we can get a sector every 10 milliseconds, then our disk performance is going to be 512 bytes every 10 milliseconds. Let's see, that's 512 is half a kilobyte. So 0.5 KB every 10 milliseconds. So let's see. This milli over here is 10 to the minus third, so it becomes a 10 to the third on the top. So we have 0.5 times 10 to the third kilobytes over 10. We have 10 to the third. Let's see, we'll take that away. That becomes a 10 to the second. 0.5 times 10 to the second kilobytes. 10 to the second is 100. So we have 50 kilobytes per second. Now, to be clear, what I'm talking about is if we got data off the disk by moving the seek arm every single time, and every single time only getting one sector, then that disk would operate at 50 kilobits a second, 50 kilobytes per second. That's slower than molasses. That's slower than some modems that I own. It's certainly slower than your cell phone plan, if you have a cell phone plan that's at least that's less than 5 years old. So, here's something important to keep in mind. A disk is not really a random access device. If we take a disk, split up into pieces, and every time we go to that disk and try to get something from a random place, that disk is going to be so slow as to be almost unusable. So what are we going to do about that? Well, there's one easy thing we can do, and then there's some complicated things we can do. I'll do the easy thing first. Okay, here's the geometry of a disk, like a bunch of pizza slices. And if one sector is one of these guys here, the simplest thing that it can do is move data in larger chunks. So the thing that we're going to do is almost every disk, it's very unusual to actually get 512 bytes off a disk. Instead, what we're going to do is group sectors together into multiples and call that multiple a block. So here's one block of data on a disk. Now, the block size can change depending on how you set things up. But most commonly, I/O systems use a 4 kilobyte block size, which is 8 sectors at a time. And if we do just that, then we can move data off this disk about 8 times faster than our super slow way of 1 sector per seek. Now that's the simplest thing we can do. Every file system starts by doing that, but we're going to have to get more complicated. Now, here's the key idea. Here's the more complicated thing, number 2. What we're going to do is try to schedule our accesses to the disk so that we get things in more of a natural order so that the seek arm doesn't have to go back and forth every time. Remember I said this was asynchronous over here? Well, the operating system doesn't really send one request to the disk at a time. If we can get the operating system to send many requests to the disk at a time, then the disk will have an opportunity to put them in an order that is going to get it better performance. And the simplest approach we can do is to say, let's try to put things in an order so as to minimize the amount of distance that this arm has to travel. If we can do more work with less arm movement, then we'll be able to get a higher throughput out of the disk. Now, how high can we go? Well, I'll tell you the limits. If we're using a SATA interface here, the electrical limits of the SATA interface are about 3 gigabits per second. That is a lot of data. That's the fastest we can move this over these wires, just as defined by the electrical limits. Now, I pulled up a data sheet for a recent disk here. You can find these online, or they may even come with the box when you buy a disk. This is the data sheet for a Seagate Barracuda disk, and it tells me the seek time and the performance and all that. And for this particular modern disk, it tells me that the SATA interface can move data at 3 gigabits per second. The controller itself can't go quite that fast, but it can move data at about 1 gigabit per second. Now again, it's not the speed to access the disk, but rather the speed to get things in and out of this memory here. So that's interesting. So if the operating system wants to write a large amount of data, this data can be transferred very quickly into this memory buffer here, where it will stay until the disk has an opportunity to move it to the physical device. All right, so we've got a long way to go. We start off with a very slow physical device. We have a fast buffer here, and now we have to figure out how we're going to schedule the activity of the disk so that we can get our data on and off in a reasonable manner. All right, let's look at how a disk might go scheduling multiple requests in order to increase its throughput. Now, to study this, we're going to introduce a simplification which is known as logical block addressing. You've already seen that a disk has a complicated geometry that consists of sectors and tracks and all that sort of stuff. But it's inconvenient for the operating system to know all of this stuff, especially since it changes dramatically between disks. So what we're going to do is introduce an abstraction which is known as a logical block addressing, or LBA. And the idea of LBA is that we're going to take all the blocks on the disk and just pretend that they are in a linear order, going from the 0th block on the disk up to some large number. Let's say there are 1 million blocks on this disk. Now, what we're going to do with this ordering is put things in order such that things that are close together in the linear mapping are also close together in the physical arrangement. So, for example, I might take the outermost track on the disk and make that outermost track the first sequence of blocks in the LBA. And then I'll go in one track, go around one more time, and make that second track the next sequence of blocks in the LBA, and so on and so forth until I get to the final track of the disk. And that way I can make the general assumption that things close in the LBA are close in performance. Now, to be fair, it's not perfect, because these two things here are close together because they're on the same track, and now at some point I'm going to jump from one track to the next, so there's a bit of a discontinuity here. But as a general assumption, it holds that things close together in the LBA are close together in the physical disk. Now, imagine that my operating system is going to issue a large number of read or write requests to the disk. So suppose that the requests get issued in this order. Let's see, I'll have request number 1 right here. And then request number 2 is kind of close next to it. And let's suppose request number 3 is way over here. Then we'll come back this way. Here's request number 4, then 5, 6, 7, and 8. Notice that that number is the order in which the request arrived, not the location of it. The location is given by its position on the LDA. Now, I have to decide in what order, I should say the disk has to decide in what order it's going to service these requests. And we could come up with a variety of approaches. The most obvious approach to try is FCFS, or first come, first served. And what I can do is draw a sort of timeline of how the scheduling strategy would traverse the disk. So we'll have time going this way, and we'll make the x-axis here the logical block address. Okay, so if I'm going to serve request number 1, I'll be over here, and then I go over here to request number 2. Request number 3 is way over there, so I'm going to seek way over here, and then back here to number 4. And then let's see, 5 is here in the middle. Here's 6. Here's 7. Here's 8, and I'm done. Let me put some numbers on those. Now, you can see, because we serviced the requests in the order in which they came, we ended up zooming all over the disk, in fact, traversing the whole length of it in order to service each of those requests. And you can see some of those had a very large seek distance, and they're presumably a large seek time as well. So here, 1 and 2 are close together, but we're going to zoom all the way over here to get number 3, and we have some big leaps over here as well. Now, we didn't have to do it in that order. Because the operating system sends a bunch of requests at once to the disk could have chosen something else. In fact, we might try to pick the request that is closest to where we are when it arrives. So we might call this shortest seek time first, or SSTF. Right, so let's suppose that requests 1, 2, 3, 4, and 5 came in first. Right, so if requests 1, 2, 3, 4, and 5 came in all at once, then we would service 1, and then 2, and then 5, and then 4, and then 3. Kind of got all those in one sweep. And then let's suppose 6, 7, and 8 came in later. Then we could come back here and get 8, and 7, and 6 all at once. And that looks pretty appealing because now we've covered a large number of requests by just making 2 swipes of the disk. And whenever we went in, we picked the thing that was the closest. Now, as you can probably guess, in operating systems, anytime we do something greedy, we can get into trouble. And greedy is, in algorithms, generally means doing the easiest thing right away. SSTF can get you into trouble if there's a constant stream of requests coming in. So if I were to continue this, suppose we had a couple more requests that were sprinkled over on this side of the disk. What SSTF would do would be to constantly serve the one that was closest to it. It might constantly serve the request closest to where the disk arm is right now, which is fine, it goes fast, but you might end up with a request way over here that never gets serviced because the disk arm is so busy trying to do all of these requests close to it. So if there's a request out here that never got serviced, this is known as, you guessed it, starvation. All right, so how can we accommodate starvation? Well, what we're going to do is instead of thinking about the request, let's think about the disk. I think it should be clear as if you look at this disk for a while, it's clear that the most efficient way to operate it is to simply have the disk going back and forth and getting as many requests as it can in a single pass. Almost like a windshield wiper going back and forth. You know, if you watch a windshield wiper in the rain, it goes this way, and as it's going this way, things sprinkle up here, but it gets them on the way back. And as long as we keep going this way, this is about the most efficient way that we can use the disk. All right? And this algorithm is known as scan, or if you like, the windshield wiper algorithm. And in scan, you'll see we always proceed in one direction until we've exhausted all of the requests going in that direction. Then we come back in the other direction and pick up the requests that were outstanding in that way. And then we go back and forth and back and forth and back and forth. So scan works pretty well. It uses the disk very efficiently. The only slight problem with scan is that it results in different parts of the disk being treated unequally. So what you'll see is that at any given time, the ends of the disk end up getting better service because they get 2 passes in short order, whereas the middle of the disk has a very large time between visits. And this can result in trouble, especially if you decide to put an important data structure in the wrong place on the disk. And so what ends up happening in practice is an algorithm known as circular scan, or C-scan, in which the disk arm will proceed in one direction, pick up all the available requests, and then, as quick as it can, scan back to the beginning, jump back to the beginning, and then service requests in the same direction again, and then repeat that. And by doing so, we avoid starvation, but we also avoid treating any part of the disk unequally so that every part of the disk gets the same amount of service. Now, in the old days, these algorithms were implemented in the operating system. The operating system had that 4 or 5 wire control to the disk directly and would know the geometry and know exactly what to do. But in a modern system, as I pointed out, all of this is controlled by the electronics of the drive itself. And it's mostly the job of the operating system to just get as many requests to the disk as it can so that the disk can make the best decisions possible. Now, the thing to keep in mind here is that if the operating system gives the disk a large amount of work to do, there's no guarantee that it's going to happen in the order that the operating system issued it, precisely because the disk is going to use its discretion to reorder things for efficiency. So, the operating system sends multiple requests to the disk. They will come back, the results will come back sometime later, possibly in a different order. And so now the objective of the operating system is to figure out how it can maximize the number of requests that go to the disk so that it can get the best possible performance coming back. All right, so now you know something about disks. There are 2 more storage devices that you should have a passing familiarity with. One of them is the CD-ROM. And the CD-ROM is actually structured very much like a disk. You all know what a CD looks like. Logically, it's structured like a disk in that it is divided up into tracks and sectors, much like the pizza slices that we talked about. It's just that instead of having a magnetic surface, it has an optical surface. And that optical surface consists of a large number of either pits or no pits, each representing a 0 or a 1. And each of those pits is burned into a reflective medium using a laser, right? So when you record something on a CD-ROM, it's just your laser pulsing at exactly the right places to either make a hole or no hole in order to make a bit pattern. Then each sector is 2 kilobytes, so they're a bit larger than magnetic disks. But apart from that, a CD-ROM actually looks electronically a lot like a magnetic disk, and it plugs in via a packet interface. And apart from not being able to write to it ordinarily, it operates almost exactly like a magnetic disk. The other thing you should know about is tape. Now, tape has been around a lot longer than hard disk drives. And here I have you've probably seen these in movies. I have a length of some reel-to-reel tape, sort of thing that used to get used in mainframes. And the way tape would work is that you would have one reel with tape here, and then another empty reel over here, and these 2 would spin together to unroll the tape and collect the excess in another roll over on this side. And then between the 2 would be a read-write head right here that would let the tape pass through it, and as it passed through it, it could either sense or make magnetic patterns in the tape. Now, at that very low materials level, tape is a lot like disk. It's just a magnetic medium, and you can either put patterns into it or read the patterns off. But the big difference is that it is completely sequential. A tape is logically one string of bytes from the end to the other, and although it is possible to rewind a tape, it is really, really slow. And so when you access it, you want to treat it linearly. Now, like a disk, tape is divided up into sectors of a fixed size, typically 512 bytes. And when you want to write some files to a disk, the way that you do it is you write a little sector that first describes the file. Here's my file called My Poetry, and it's 2 million bytes long, and I'm the owner, and here are the permissions, and all that information goes into this header block. I'm sorry, this header sector. And then you follow that up with sectors containing the actual data of the file until you've written out all of the data. Once you've done that, then you go to the next sector boundary and you write out the next header to represent the next file that you want to write. Now, as you can see, if you know what file you want to read, you can read it pretty quickly because it's always sequential access. So as long as you mount the right tape and start it in the right place, you can move data off tape, sometimes even faster than you can move it off of disk. Writing it is a little tricky because first you have to decide which files you want to write and then generate the headers appropriate to those files. And Unix comes with a tool exactly for this purpose, and the tool is called tar. I'm sure you've used tar before. Tar stands for Tape Archive. Tar takes a list of files and writes them out in this format. And if you have a tape, it'll write them out to the tape. If you don't have a tape, tar will take that list of files and write them out to a new file that contains all the files as a package. And of course, we use this today to upload and download large number of files as one bundle, and we call the file a tar bundle. But originally, it was used for tape. Now, over the years, nobody uses tapes like this anymore, but tapes are still used for a backup because they're quite a bit less expensive than disk and have a longer shelf life because there's fewer things to break. And so nowadays, you might have a tape that comes in a little cartridge like this that has the full tape and the empty tape, and just sort of nicely packages it so it's easy to take in and out. And then you just have a tape drive that you plug this into, and then the motors whir away, and you can read off data in the order using the tar format. So tape is still used for cold storage and backup for things that don't need to be accessed on a regular basis. All right, so now you know the basics of hard disk drives. I think the main thing that you need to take away is that because it's a physical device, it takes time to move that arm back and forth, and so much of the work of the operating system has to take that into account. Tapes and CD-ROMs and other storage devices also have similar concepts of blocking I/O, but they have different performance properties. And so when you organize a program, you have to take into account the performance properties related to the geometry of the device. All right, I think that's it. If you haven't done so, read the chapter. It's good stuff. There's more things in there than I explained. Apart from that, have a great weekend. Start working on Project 5, and I'll see everybody on Tuesday. Okay, bye-bye.